Welcome to The Explainer. I am so excited to unpack today's topic with you because honestly, we're looking at something sitting right at the absolute bleeding edge of computer science. We're diving into a breakthrough study recently published in SN Computer Science, and it tackles one of the biggest, most pressing bottlenecks in modern tech. How? By using a completely new computational paradigm. Basically, we're going to explore how we can fuse the absolute best of classical computing with the staggering, almost mind-bending potential of quantum mechanics.
But first, I want to pose a question directly to you. What actually happens when our data simply outgrows our classical computers? I mean, really think about it for a second. We have these modern AI datasets for things like natural language processing and massive computer vision models, and they are literally exploding in size and complexity. Because of this, our traditional supercomputers are being pushed to their absolute breaking points. The stakes here are massive. We are quite literally running out of standard computational road.
Okay, let's dive right into this. Here's our roadmap for today. We'll start with the curse of dimensionality, followed by the quantum noise problem. Then, we'll introduce the hybrid tag team, look at benchmarking the bQCNN, cover mitigating quantum hardware noise, and finally wrap up with the future of AI.
All right, moving right along to Section 1, the curse of dimensionality, and how we're hitting the classical wall. To really understand the urgency here, we have to look at the current crisis. As our datasets grow exponentially larger, our massive classical models hit intrinsic physical limits. It's kind of like trying to find a needle in a haystack, except the haystack is doubling in size every few seconds. We're facing staggering computational costs, completely bloated memory footprints, and massive parameter scalability issues. The published research refers to this as the curse of dimensionality. Basically, to get even a tiny marginal bump in performance on highly complex data, classical models suddenly require an exponentially larger amount of resources. It's just an unsustainable trajectory for the future of AI. Which brings us to Section 2, the quantum noise problem, or promise versus reality. So you might logically be wondering, well, if quantum circuits are so insanely powerful, why don't we just ditch classical computers entirely and use quantum for everything? Well, putting the two side by side reveals a pretty huge catch. Classical machine learning, as we just saw, hits a wall with polynomial or exponential parameter scaling. Pure quantum, on the other hand, offers a theoretical logarithmic scaling. That means it needs far, far fewer parameters as your input size grows. Sounds absolutely perfect, right? But pure quantum is severely crippled by physical reality right now. It suffers from hardware noise, extremely short coherence times, and a massive issue known as the barren plateau phenomenon. This is where loss function gradients basically decay exponentially as the quantum system size grows, which, well, it essentially renders the whole model entirely untrainable. To really grasp why pure quantum just isn't ready for prime time yet, we have to define the era of computing we're currently living in, the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum. These are the physical processors built right now, today, by companies like IBM, featuring tens to maybe hundreds of qubits. And yeah, they can execute computations well beyond classical simulation, which is amazing. But they suffer from short qubit coherence times and highly erroneous gate operations. We simply do not have fault-tolerant, perfectly noise-free quantum computers yet. That's just the reality of the hardware. So how do we fix this? Let's look at Section 3, the hybrid tag team, combining brain and brawn. This leads us directly to the huge breakthrough from the source paper, the Hybrid Quantum Classical Convolutional Neural Network, or HQCNN. So the crucial point here is that we actually don't have to wait decades for perfect quantum computers to see a massive benefit today. We can just use a tag team approach. The quantum processor acts as the brawn. It goes to work exactly where it excels, creating highly entangled states, mapping data into massively high-dimensional Hilbert spaces, and handling super complex nonlinear feature extraction. Then, the classical processor steps in as the brain. It takes over to do the heavy lifting of data manipulation, optimizing the circuit parameters, and making those final classification decisions. It's brilliant because each technology is doing exactly what it's best at.
But how do they actually connect? Well, to successfully bridge classical data inputs into a quantum circuit, the researchers rely on a very precise three-step pipeline. First up is standardization, basically scaling the features to have a zero mean and unit variance. Next is normalization, which scales image pixels to a simple 0 to 1 range. But step 3 is where the real magic happens, quantum feature mapping. This actually expands the feature space using nonlinear mappings like radial basis functions and phase encoding. This allows the quantum circuit to properly digest and actually leverage those incredibly high-dimensional data correlations.
Now let's get into the results in Section 4, benchmarking the bQCNN, because the proof is in the data. Shifting our focus to the actual empirical data, the researchers tested a specific, highly optimized model called debranched QCSN, or bQCSN. And the results? 93.6%. Just take a second to let the magnitude of that performance metric sink in. This is a massive breakthrough top accuracy achieved by the bQCSN model on the standard MIST dataset.
And this brilliantly illustrates exactly where that 93.6% sits relative to the competition. You can clearly see how the bQCNN definitively leaves the others in the dust, outperforming both the pure classical architectures and the standard pure quantum baselines. It's a clear winner.
Let's actually break these numbers down a bit more neatly so you can track the progression without getting lost in a soup of statistics. A standard classical CNN achieved an 88.2% accuracy. A pure quantum CNN bumped that up slightly to 90.1%. But then, the hybrid bQCNN leaps all the way to 93.6%. And that's alongside vastly superior F1 and precision scores sitting well above 0.9. Now, why does this matter? It matters because it proves the model isn't just making lucky guesses. It's highly, highly reliable. By leveraging quantum entanglement for feature discovery and classical depth-wise structure for decision-making, it literally captures the absolute best of both worlds.
But here's the kicker. It is not just about raw accuracy. It's also about sheer training speed and efficiency. The hybrid bQCNN reaches its target loss threshold and converges in just 3 training epochs. 3. The classical baseline, it took 11 epochs to hit that exact same mark. The hybrid model reaches its peak performance dramatically faster, and that's because stable gradients propagate seamlessly across the quantum circuit. Basically, the system learns with incredible speed.
And all of this builds into an undeniable structural advantage. When you look at how the data clusters, it's wild. The quantum feature mapping dramatically expanded the space. In fact, the quantitative analysis from the paper reveals that these quantum feature maps enhance the interclass separation by an astonishing 87%. 87%. The quantum transformation is essentially untangling all this complex, messy, overlapped data and turning it into easily separable clusters that the classical brain can quickly categorize. Moving on to Section 5, mitigating quantum hardware noise, or silencing the distractions. Now, while those numbers are seriously impressive in a simulation, we do have to address the practical reality of deploying this on current noisy processors from companies like IBM. The researchers actually built a shield against this noise using something called zero-noise extrapolation, which is essentially algorithmic guesswork to find ideal outputs from limited noisy runs. And they paired this with ADA Boost, which is basically an ensemble of 50 decision trees acting like a panel of experts voting to improve reliability. The result of all this? These integrated mitigation strategies yielded a 15% improvement in noise resilience. It successfully maintained over 80% accuracy, even at an extreme 50% noise rate. That is huge. And you can really see the impact when looking at the decay rates. The mitigated hybrid models show a noticeably, significantly slower decay rate compared to the unmitigated circuits as the noise level cranks up. This hard data proves a crucial point. This hybrid architecture isn't just some fun, theoretical exercise on a whiteboard. It is genuinely viable and completely deployable on today's noisy hardware. Finally, let's wrap things up in Section 6, the future of AI, and a scalable paradigm. So, what does this all mean for the future trajectory of machine learning? Well, this study fundamentally proves that a hybrid tag team approach not only solves the classical curse of dimensionality we talked about earlier, but it provides a highly stable, parameter-efficient framework moving forward. The bQCNN demonstrated totally superior generalization capabilities, completely avoiding the massive overfitting that so often plagues traditional classical models. By narrowing the training validation gap to less than 0.01 at 10,000 samples, it shows that the model genuinely, deeply understands the underlying structure of the data, rather than just blindly memorizing it. Which brings us to our final, provocative thought for today. As hybrid frameworks successfully conquer the strict limitations of the NISQ era, is the true quantum revolution already here? I mean, think about it. We might not actually need perfectly noiseless quantum supercomputers to change the world, at least not if we can perfectly pair our current, noisy ones with classical brains today. Thank you so much for joining me in this explainer to unpack this absolutely fascinating research. Keep learning, keep questioning, and I'll see you next time.